This is Physics 1, Lab 5. For this lab, we took a Squishmallow and we dropped it from 3 meters and observed the amount that the Squishmallow shrunk together and compressed and squished and treated it as a spring. By using the energy principle, we can find the spring constant of the Squishmallow. So we're going to go through the physics ideas, main results, models, equations, what the system is, explanations of assumptions, results, and the meaning. For the main physics ideas, we use the energy principle. With the energy principle, we say that energy is completely conserved, and at the top before we drop the Squishmallow named Plop, it has just gravitational potential energy because the spring is not compressed yet and it is not moving yet. At the instant right before it touches the ground, it's still not compressed, so we know it has just kinetic energy and just gravitational potential energy. And then as it fully compresses, we can figure out the change in kinetic energy. And since we're using tracker from the top of the Squishmallow, not the middle, we know it has gravitational potential energy and spring potential energy. So the results are found by setting the change in energy equal to work and finding that that's equal to 0, and using all the known changes in energy, such as the gravitational potential energy, the spring potential energy, and kinetic potential energy, and rearranging that in order to solve for k, which I will explain more in a minute. So the models that we use for this is the spring potential energy equation, the gravitational potential energy equation, and the kinetic energy equation. So for the system, we define the system, we include pretty much everything in the system, including the Earth, the spring, the Squishmallow. So by doing this, we say that the total work and the change in energy is 0. So for this, we used just an experimental lab, as the instructions said we were allowed to do, and did not make any code because there were a lot of assumptions we had to make that would have been very difficult to include in coding. Some of the assumptions we made is that the Squishmallow is an ideal spring, and that we don't consider energy loss to deformation or thermal energy or anything like that, because those aren't things we necessarily could measure in this scenario. So for the results, this is all the equations that I use in order to solve for the spring constant. At the top, I show again that the only energy we have is the potential gravitational energy. I show what that's equal to and the answer I got for that. At the bottom, we know we have spring potential energy, gravitational potential energy, and kinetic energy, but at the instant right before it touches the ground, we can use that as the initial velocity right before it fully compresses, since we're defining at the bottom the change being right before it touches the ground and right after it touches the ground and squishes all the way. So the final velocity when it fully compresses is 0. The initial amount of compression is 0 right before it starts compressing, and MGH, since when we're using tracker, we measure from the top of the Squishmallow, not the middle, because we need to use that to consider the spring length. It does have a slight gravitational potential energy, so we plug in all of the known values for those and solve for the spring constant and get 207.28 newtons per meter. So the spring constant of about 200 newtons per meter means that it has a stiffness of about 200 newtons of force to be applied per meter of compression. I was expecting a slightly smaller number, a less stiff spring, considering a Squishmallow, for those who know what a Squishmallow is and have touched it before, it is very squishy, and it compressed a lot very quickly. But the fact that it is a little bit too large does make sense, considering the assumptions we did make in the potential sources of air, because we don't consider any changes in internal energy or deformation or thermal energy changes, because those aren't things we could measure, and if we had included those, the amount of spring energy would have been a little bit smaller, and the spring constant therefore would have been smaller also. Thank you for watching.